So first, about the exam we just took. I am grading it. I created a rubric. I think you can see it. And this time, it's very hard to grade one problem at a time. So I'm actually, based on the rubric, I'm going through, I mean, I just pick a student at random and I move on. I think I have what is it? 10% done right now, 20% maybe. So I'll be getting there. So we'll be, hopefully by next class, it will be graded. And you can see it, and you can see the rubric and how is it, what is it that you didn't get right. Then next one, the wiki for 7.3. Yeah, I'll do it right after this class. And then let's talk a little bit about the final exam. Let me just check. What is it that we agreed with the math department? Just a second. Okay, so the final will be, we'll put it up May 12th at 1 p.m. and it will be 24-hour exam, all right? So it will be similar format to the two exams that we have done, with the difference that it is cumulative. It includes everything, and it's a little bit longer, right? It's supposed to be a 2-hour exam had it been a live exam. So I will base it on the previous times that I have taught this class, so it will be exactly like that. And you could use as a guidelines the two exams that you already have. So I won't have. So of course the chapter 7 is not. It has not been covered in any of the two previous exams. So for sure there will be problems from chapter 7 that will be featured in the final exam. So expect that will happen. And I expect to have a bit of time next class for us to quickly review, or get an overview of the entire semester. Okay. So that's how the exam. Does that answer your question? Who asked the question?
Yes, you answered it. Thank you.
Okay, awesome. Very good.
Just to clarify, you said 1 p.m. will be the upload time instead of 12 p.m. or did I miss here?
It will be available at 1 p.m. and it will you will have 24 hours. So from May 12th to May 13th.
Perfect. Thank you.
Yeah, and I suppose nobody had any troubles with the Zoom and everything, right? I mean, I think it went smoothly. I checked the times that you guys uploaded, and you guys, I think, have plenty of time. So far it's looking good. I mean, everything that the few that I have rated all have gotten like 80% or more. So it's looking good. Okay, good. So let's continue where we left off. We were talking about integration. Let me go towards the book. Specifically, we were going to talk about this theorem right here, properties of the integral. So let me mark it right here. So this, what color is this theorem right here that I'm boxing in red is the one we want to take a look at. And so we'll go through. We want to do everything here. Some of these are meant to be done by you as homework exercises. Get some practice, or they're actually quite straightforward. So let's start with, so let's go through this. So beginning with 1. So 1 actually is one that we won't do. It's simple. The sum of the integrals equals the integral of the sum. It's the simplest of them all, and it's one of our exercises. So 1 is exercise 7.4.5. So you guys are going to do that one. So we're gonna start, we'll talk about 2, and I'll actually give you 2 ways of proving 2. So 2 is that you can take a constant out, and that the function, when you multiply by a constant, is integrable. All right, so that's what we want to do. So for k in the real numbers, kf is integrable, assuming f is, as the overarching assumption, and the integral of kf is k times the integral of f. So let's take a look at that one. So this one over here is the one we want to prove. Actually, first I wanted to, like I said, I'm gonna do it 2 different ways. I think the book does it the first way. I'm gonna do it. Let me just briefly check. I had it in my notes, but yeah. So I'm gonna do it 2 ways. One, essentially like the book, and the book. Remember, what is it? What was our philosophy in this entire semester? Actually, we started with sequences, right? Right from the get-go, we learned about sequences. So we develop a lot of tools with sequences. So it makes sense to use those tools whenever we have the chance. So whenever we want to prove a limit, we should think about the sequential interpretation of a limit. Remember that? So we should remember that. So let me put it here. Recall that. So when we talk about a limit of a function, so the limit of doesn't even need to be a function, right? A limit in general, but yeah, let's use a function. This limit is L when x approaches c, if and only if for every sequence xn that approaches c with xn not equal to c, the limit of the fxn equals L, right? So if you use this interpretation that you can change a limit with the fact that it happens for every sequence that has the property of approaching C, then you can use all the theorems we know about sequences, right? So here in particular, what is it that we know? So we know that f is integrable, right? So here we know f is integrable on AB. And we have an integrability criterion, which is great, right? So what is the meaning of being integrable? What it means that the upper integral equals the lower integral, which means the supremum of the lower sum equals the infimum of the upper sums, right? They meet in the middle, right? But we developed this criterion that is more helpful. This means, so this is if and only if for every epsilon, there exists a partition P epsilon such that the U of this partition minus the L of this partition is less than epsilon, right? So we know this. So using this, there is an exercise in the book. So let me put it right here. So it says, it's exercise 7.2.3. In fact, let's put it on the screen. So let's look at exercise 7.2.3. Is before, right here. It's called sequential criterion for integrability. And what does it say? Let's highlight it or mark it. So it says that right here, if you have a function that is integrable, if and only if there's a sequence of partitions with this property that the limit of the U minus the L is 0, right? And in this case, the value of the integral equals the limit of the u or the limit of the L, right? Whichever one you want. So it's this next one after this. So this continuation, all right? So, and I'm sort of outlining how you could prove this, right? How could you prove this exercise? Well, you could use, so what is it that we have here? See, we can, using, let's go back to the page. Using this criterion for integrability, you can use as your epsilon, say the sequence 1 over n, right? So for the sequence 1 over n, you're going to have that there's a p sub 1 over n, you can call it pn, such that this happens, right? So if you use the sequence 1 over n, you can prove that if the function is integrable, then this happens. And the reverse, if you have that it happens that you have a sequence where the difference approaches 0, that means by definition that for every epsilon you can make this as small as you want, which would mean by the integrability, regular integrability criterion, that f is integrable, all right? So it's almost straightforward. It almost feels like this one on the top, that this translation from regular limit to limit by sequences. It's essentially that. So the only part that is additional here is to show that you can get the value of the integral with the value of this limit or the value of that limit, right? And that is, again, easy. So let's suppose that we have that. So like I said, I'm not giving you all the details here, so there's parts for you to complete. So I'm just going to write here, use this to prove that f is integrable on AB if and only if there is a sequence of partitions Pn such that the limit when n goes to infinity of the Pn minus the L, so the upper sum minus the lower sum is 0. So that's the part that I just outlined how you could do it. Very, very straightforward. Now, I'll do the other part. I'll do the other part. How about, how do we check that if this happens, then this limit or that limit, whichever of the two, is actually the value of the integral? Yeah, this is how we do it. Well, yeah, this is what's going to happen. So recall that. So assume, so let's suppose that this limit is indeed 0. So you have one of these functions that is integrable, right? And pick an n such that this makes this less than epsilon. So let epsilon be greater than 0. And pick n such that this difference is less than epsilon, right? That's the definition of this limit being 0, by the way, right? That's the only thing that I'm using there. Okay, so then what I want to do now is to remind you of some simple inequalities. See, here we go. So the value of the integral that we want, remember what this guy is. This guy is both the upper integral and the lower integral. So in this particular case, I'm going to use the upper integral. This is the u of f. Now let's remember what this stands for. U of f is what? Is the infimum of all of these guys. So in particular, it's a lower bound for all the upper sums. So this is less than or equal u of fpn for sure, because this is the infimum. So it's a lower bound. And then because of this inequality on the top, so let me call this one star. So by star, this is in fact less than the L plus epsilon, right? And so we put this all together, right? What we have is that this number, so this difference, by the way, is also positive, right? So this, where is it? The, yes, so, oh, I'm missing something here to explain that precisely. So also the L, the lower sum, is of course smaller than the lower integral, because the lower integral is the supremum, so it's an upper bound of all of these guys, and this is this guy, right? So this shows to you that this difference, when I do this minus that, so the integral minus the L is positive. So take a look at these two inequalities, and I'm going to put them together. What do they say together? It say that the integral minus the L, this one over here, is positive, greater than or equal to 0. That's this one. But using that one, it's in fact less than epsilon, right? So then this by definition means that this limit is 0 when n goes to infinity, right? That's precisely the definition, because I could do this for every epsilon. So this implies that the limit when n goes to infinity of this integral minus the L is 0, right? But this is a constant, it's just a number. So this means that the limit of the L's is in fact the integral, right? And that's the additional part that I was trying to prove. And once you know it for the L's, right? If you know that this the limit of the L's is the integral, then you know it for the U's. So you can repeat this process again, or you could simply use the fact that, let's go up to the top, that this limit is 0, right? This limit is 0, and we already know that this limit approaches the integral. Then what does the other one approaches? Well, the integral as well, right? So we don't need to repeat all this argument. So I'm just going to write here at the bottom, since the limit of the U minus the L is 0, it follows that the limit of the U's is also equal to the integral. Okay, all right. So we did a bunch of work. This work, by the way, is really, we're talking about 7.2.3, really. I haven't even worked on the problem we wanted to do, right? Let me go back to what we wanted to do. So this is what we wanted to do, that if we have a function that is integrable, we can take the constant out, right? So now I'm going to work on that, but I'm going to use this property that we just developed, all right? So let me get another piece of paper here to put on top, so we can see what is it that we're doing. So right here. Okay, good. So now let's do this. And I'm going to do it for positive k. The negative k is similar, but you need to reverse. So there's sometimes you multiply by a negative number, the inequalities are reversed. So it needs to be worked out separately. And it's not that it's more difficult, it's that you need to do it separately. So let's do positive k. So assume k is greater than 0. Okay. Now here's the thing. So this, you should realize that this clearly happens. So observe that if you do u of kf with respect to any partition, well, what is this one? Let's remember what this stands for. What is this one over here? It's a sum, right? Depending on the partition, right? If the partition is traditionally the xi's, so this is from k. Can use k now. Let's use j. From j equals 1 to n, right? And then we have the m j, right, times x j minus xj minus 1, or the length of the jth interval. And mj is the supremum, right? So mj is the supremum. The supremum of what? Well, we're using this function, the supremum of k f of x, such that x belongs to the interval xk minus 1 xk. And now we're gonna go really back and remember what happens to a supremum when we multiply by a constant. By the way, we had this as our problem in our first exam, right? So let me put a parenthesis here. So on our first exam, didn't I ask you to prove that, to show that the supremum of 2a was 2 times the supremum of a, right? And the way you did it is you can exactly do it with a positive constant k instead, right? So this was a particular case of a more general problem where you are asked to do it in general. So that's exactly what we have here. So this supremum over here happens to be the same as k times the supremum of just the f. So in other words, you can take the k out of the supremum. And this is where you need to be careful. If k was negative, then this property is not true. If you multiply by a negative number, then the supremum is replaced by an infimum. So then an upper sum becomes a lower sum. So that it's a little bit more complicated, but not that, you know, it really is just the same idea. So this is important that k is positive. And then once you realize that this is true, that you can take the k out, then this becomes, let me call it this, k times mj prime, where mj prime is this supremum, okay? Mj prime is this guy over here. Okay, so then this upper sum becomes k times this other upper sum. So this other upper sum is exactly the upper sum for just the function f, right? So this is k times the upper sum of fp. And this is the property that I want, right? So similarly, I'm not gonna do it again, but it works the same way. The L, you can take the constant out, right? And then, now we can use the property. So thus, if we want to do this limit, the limit of the upper of kf pn minus the lower of kf pn, whatever pn is, right, for an arbitrary sequence of partitions, well, according to the properties we just learned, we can take the constant out. So this is k times the limit of ufpn minus lfpn. So if this guy is 0, because the function f is integrable, right? The function f is integrable means there's a sequence that makes this limit be 0. So if this limit is 0, then I'm multiplying here by 0, which means this limit is 0, and this means this function kf is integrated. Hence, kf is integrated on AB. All right? So we're done with half of it. Now we only need to find out what is the value of a function. So, and that's also super easy, right? So what is the value of the integral kf? Well, let's see. Further, you want to know the value of the integral. Well, what is this? This by definition is, which one I'm gonna use? The limit, right? Is the, let me go back to just momentarily, bear with me. So what is it that we prove about this? That when this happens, when you have a sequence that the difference approaches 0, the limit of the u's or the limit of the f's That's what we did over here. The limit of the u's is the integral, and the limit of the else is also the integral, either of the two. Okay, so that's a property I'm going to use here. So this is the limit, and just pick one. I mean, the u or the f really doesn't matter. So I'm going to use the upper sum just because. So this is the limit of k f of the pn's. But we know we can take the k out by this property on top, right? And the k comes out of the limit. And we know that this limit is actually the integral from a to b. So this is k, the integral from a to b of f. And that's it. This shows that not only is kf integrable, the integral of kf is k times the integral of the f. All right, so that's proof, the first proof. Now, if you want to use this sequential criterion, the PN. Now, say you don't want to do it. You want to do it straightforward. Can it be done? Yes. And I wanted to show you. I mean, I know that I'm like beating this problem to death, but that's okay. I wanted to show you different ways of doing the same thing. So you don't need to do it. Not all the solutions need to be the same, right? So let's say you don't want to use sequences. You want to do it directly. Can it be done directly, Professor? I don't want to use sequences of partitions. Yes, it can be done directly, right? So second solution, no sequences. Okay, so what is it that we're going to use? We're going to assume that f is integrable. I think the correct pronunciation is integrable, but I have problems because in French it's integrable, and then and so it's in Spanish. So that's but the correct pronunciation is integrable. Sorry for that if I'm confusing you with that little tidbit. Okay, so suppose this is integrable, and then what does that mean? Well, this means that for every epsilon, there exists some p partition such that the u minus the L is less than epsilon, right? And we're going to use that. And then we can use any epsilon here and then multiply it by a constant. So we're going to need over k. So I'm going to put over k already, right? And then what? So we know this. Then if you want to calculate the same but with kf, well, we already learned that we can take the constants out for positive k. So I'm using positive k here, by the way. If you're using a negative k, the thing flips, all right? So for positive k, this upper sum is actually k times u of fp minus k times L of fp, which is k times u of fp minus L of fp, which is less than k times epsilon over k. And we're done, right? This difference is less than epsilon, and I can do that for an arbitrary epsilon. Therefore, by the integrability criterion, kf is integral. Kf is integrable. Okay, and then the only issue is what is the value of the integral, right? So how do we do that part without the limits? And it's not that difficult anyways. So here we go, further. If you want to do the value of this integral, kf, this k. Well, this is for sure. So in fact, equal right here. This is equal to the upper sum of kf. Right, it's the upper integral of kf, and this guy is the infimum. So because it's the infimum, it's less than or equal a particular one, in particular this guy, right? The ukf of p. And then we can take the constant out, right? And then we know that this one satisfies this, that UF of P is less than epsilon over K plus LF of P. So this is less than K times epsilon over K plus LFP, right? This is epsilon plus K LFP. Now here we know we can take the constant in. So this is epsilon plus, oh, we don't see anymore, plus LKFP, right? And, well, this is the lower sum. So the lower sum is less than or equal. So I'll continue over here. So this is, let me repeat what I have here. So same idea, right? This guy over here is by definition the lower integral is by definition the supremum of these guys. So this is less than the epsilon plus L of Kf, right? Because this guy is the supremum of all of these, and is equal to the integral. Should I not taking out the integral? Oh, I didn't. Okay. My bad. I did something that I didn't want to do. I mean, it's not that it's incorrect. It's just I didn't want to do it. I didn't want to put the K inside. So let's remove this last. And then over here, I don't have the K inside. Keep it outside. So I want to compare to the other integral, right? So we leave the K outside. The same argument. It's the same argument, but then here the K is out. And this shows to me that the integral of Kf is less than or equal the epsilon plus K times the integral of f, right? So let's keep that inequality here. So i.e. the integral of Kf less than or equal epsilon plus K times the integral from A. That's the one we just proved, okay? And then we can do the same thing with the so repeat the argument. Let's do it. All right, let's do it all together. Let's see if we can show the everything that we need here. Let's repeat the argument, but now we're gonna start with the L. All right, so here we go. So we start from Kf, and Kf is the lower integral of Kf. Now lower integral is a supremum, so it's greater than or equal L of Kf. You see how I'm copying the argument? Now here we can take the K out. We learn about that. So we do that. Now by our inequality on the top, the L is actually now greater than the U minus epsilon over K. And this turns out to be Ku minus epsilon. All right, and then, so this is, let me copy again over here. So this is minus epsilon plus Ku, but it looks exactly like the one we did before. Now, this one is by definition an infimum. So this happens, it's greater than or equal the U of f, and this is the value of the integral. All right, so altogether, what do we have? We have that the integral of Kf is greater than or equal negative epsilon plus K times the integral of this one. Okay, and you put these two together, and what it says is that the difference of this is AB Kf minus K AB of f, the integral from A to B, that difference is on the one hand greater than or equal negative epsilon, on the other hand less than epsilon. So it means that the absolute value is less than epsilon, right? And because this happens for every epsilon, this number better be 0. Because this is true for every epsilon, follows that. This is true, right? So now that you see both ways, what do you think? Well, this part to me was more complicated than the way we did it, right? With the other one, we simply had to apply the limit when n goes to infinity, right? So look, we had to do these two inequalities, whereas with the previous way, all we had to do, I'll show it to you right here, all we had to do was to do this limit, right? It was super easy. So on the other hand, the first part was a bit, actually no, the first part was also really, really easy, right? So this solution, the first one is way more straightforward, right? It's cleaner and quicker. Of course, we had to first do this sequential criterion that I showed you earlier, right? But once you knew that, this solution was way faster than considering all these inequalities. Okay, but you still can do it this way if you choose to do so. So we're done with this one. All right. Okay. So I know we're taking a bit more time on this that you probably expected, but that's okay. We want to learn how to do this properly. So now let's take a look at the other properties. So for our other properties, move on to our page what we were working on. So we're right here. So the next one is this one. If your function is between little m and big M, then the integral is between m little m times b minus a and capital M times b minus a, right? And this one has a simple way of remembering it if you draw a function, right? So let me go to the page and show you what I'm talking about. So if you draw a function, something like this, from A to B, right, and you know that the area under the curve represents the integral, then you can look at the minimum, right? So what is the minimum of this function? The minimum is right over here, and the maximum is right over here, right? So in this case, we know that f of x is between little m and capital M. And what we're saying is that if you look at the area of this rectangle, what is the area of that rectangle? Is the base is b minus a and the height is m. So we're saying that the area of the purple rectangle is for sure smaller than the area under the curve, right? Clearly. And the area under the curve is for sure smaller than the big green rectangle. So this one is in turn less than or equal than the area of the green rectangle. And these rectangles have areas capital M times b minus a and little m times b minus a. And that's the property we wanted to do, right? Now, this is not a proof, by the way. I mean, this picture makes it look like it's obvious, but it's not a proof, all right? It's not a proof because this is supposed to happen for any integrable function, not necessarily one that looks pretty, like the one I drew over here, right? Continuous and smooth. So you have to make sure that your proof does not depend on the actual drawing, right? You don't want to make any assumptions. So we're gonna do it, but it's actually quite easy. So what is it that we need to do? Well, here's the proof. So in general, this happens, right? This guy is smaller than the supremum, which is L of f, and that's the integral, which is equal to the upper integral, and the upper integral is the infimum of the upper sums. So this happens for an arbitrary partition, right? So this is true for any partition. So I'm just going to use a very special partition. So use this partition, the partition that only has the A and the B. Is that clear? So what is, how do we know about that partition? Well, that partition is, so what is going to be L of FP? It only has two elements, right? So it's going to be the length of the interval times the infimum. But we already said that all of these numbers are bigger than M. Therefore, the infimum is bigger than M. So this is greater than or equal M times B minus A. And the upper sum, similarly, of this very simple partition is now the supremum. So it's the capital M. There's only one interval here, right? Times the length of the interval. And this is, we said that the function is smaller than M. So all of these values are smaller than M. Therefore, the supremum is smaller than capital M. Right, so that happens. So tag these inequalities here, and we're done. Right, that's exactly what we wanted. So just copy this inequality here and this one here. And that completes our proof. All right? Good. So that was quick and painless. Very easy to do. Let's take a look at the next one. So the next one says that if one function is bigger than the other, then the integral preserves the inequality, right? And that's also very, very easy. So this is the proof of 4. Here's what we do. Super easy. We look at the difference, right? We look at an auxiliary function, g minus f. So assume f of x is less than g of x on AB. Let h of x be the difference, g minus f. Then h of x is greater than or equal to 0 for x's in AB, right? Because this g is bigger than f, so g minus f is greater than or equal to 0 for every x. Therefore, this happens for every x. Now I could use the previous one, right? So the previous one told me that if I have a lower bound, then the is integral, the integral of the h, is bigger than 0 times b minus a, which is 0. And what is the integral of the h? Well, the h is the same as g minus f. And that's the same as g plus negative f. And by property 1, the one that I didn't do, the one that is homework for you, the integral of the sum is the sum of the integrals. So this is the integral of g plus the integral of negative f. And by property 2, we can take constants out. So this is, I can take this negative 1 out. And so I have that. But this is 0. The integral of the h is 0. So that means now the integral of f equals the integral of, so not 0, my bad, is bigger than or equals 0. Greater than or equals 0. So then the integral of the g is greater than or equal the integral of the f, right? So the inequality is preserved by this. Okay, and then 5. Let's go take a look at 5. So 5 says that the absolute value of a function is integrable, and the absolute value, the integral of a function, absolute value of that is less than or equal the integral of the absolute value function. This, you could think of this as the triangle inequality for integrals. All right. So there's two parts here, and I'm gonna do one of them. So part one is, so first check that the absolute value of f is integrable. And this is exercise 7.4.1. So you're gonna do that part, but let's assume that happens. If you know this happens, if we assume this is true, so assuming you already did that exercise, then we can continue to do the inequality we want the following way. This happens. This number minus the absolute value is for sure smaller than the f, and the f is for sure smaller than the absolute value, right? Because this guy is always positive. So if f is positive, they're the same. But if f is negative, then this guy is bigger. Similarly here, if f is positive, it is bigger than this because this one is always negative. And if f is negative, then they're the same. Okay, so this happens. So then, by part 4, the one we just did, well, then the integral of this is smaller than the integral of the f, which is smaller than the integral of this one. Actually, let me write it the way the book does, so we don't use the x, right? We keep it simple. It's just like this. There's no need to make it clunky, right? You can make it look nice, like this, right? So this happens thanks to this inequality. And this, we can take the sign out, right? So this is really minus the integral of the absolute value, and this is the integral of a function, and this is the integral of the absolute value. So these two together, what it says is that the absolute value of this one, see this number is between a number and it's negative. So that means that the absolute value of the original integral is smaller than the integral of the absolute value. And that's what we want, right? The triangle inequality for integrals. All right, questions? In fact, we have, let me see, I think we have a bit more time. Maybe we can check, let me just briefly check something. Yes, so I wanted to let you know something. So there are, so from page 231 and further, we're not covering that. So page 231 and 232, where it says uniform convergence and integration, we're not going to be able to do that because it's based on material from chapter 6. And we didn't cover chapter 6, so we have to skip that part, right? So and we don't have any problems that are about those type of issues. So we don't do anything of function convergence, limits of functions, right? We didn't do any of that because that was in chapter 6. So page 231, where it says uniform convergence and integration. Let me show you on the book. Right here. So we just did this part. And right here, starting from here, we don't do this, all right? We're not gonna cover this, sadly. The semester is crammed as it is already. So this part we're not gonna do. So I'm gonna show you just a few definitions, but I think we have more time. So maybe let's do let's give it a try to start exercise 7.4.1. We have a bit of time.
Professor?
Yes.
Are we going to cover 7.5? Because it's part of the homework problems.
Yes, 7.5 we're going to cover next class.
Oh, okay, great.
The Fundamental Theorem of Calculus. We better do that.
Yeah, because I was going to say that's the most important.
Yes, exactly. Yeah. Yeah, we'll do that next class. But again, 7.5 has more as well. So we essentially are just going to cover the fundamental theorem. 7.5 is actually quite short. It's only 2 pages, 3 pages, 2.5 pages.
Right, right.
So we'll do it next class, and we'll have plenty of time.
Perfect.
So yeah. So there's exercise 7.4.1. Let's see if we can do it. It says, let f be a bounded function, and set. See, we have these supremums. M is the supremum of the function when x is in A, and little m is the infimum. And then the prime ones are the ones that have absolute value, right? And so the first part A, says show that capital M minus little m is greater than or equal capital M prime minus little m prime, right? That, okay, it's an interesting inequality. Let's see if we can figure that out, do it somehow. And then show that if f is integrable on the interval AB, then the absolute value of f is also integrable on that same interval. That would be the thing after that. All right. So let's give it a try. Do we do that one or not? We are also going to have, let's see. Okay, so let me write it down. So capital M is the supremum of the F's. A is just an arbitrary set. And little m is the infimum with no absolute value. And then m prime is the supremum when we have absolute value. And little m prime is the infimum when we do have absolute value. And we're asked to show part A, show that. Let's see. Okay, so let's change to the right here. Okay, so this is what we want to do. How do we do this? So we have a supremum and an infimum, and we're subtracting, so this supremum minus that infimum, right? That's what we're doing. So how is it that we could do this? All right, so this reminds me of, so I wanna try to find out the best way we could do this, and this reminds me of a problem we have. So let's see if we can find it. So we go way back to when we learn about supremums and infimums, right? Which, if you think about it, is, you know, the real basic, the properties of the real numbers, right? That's what makes the real numbers the real numbers. So we go back to chapter 1, right? So chapter 1, when we learn about the real numbers, we have a problem here. Where is it? It's exercise 1.3.6, right? And it says that essentially how to, if you look at the sum of two sets, right? How to figure out the supremum of that. And that it turns out to be the sum of the supremums. So let me show you that one. So it's back on page 19. All right, right there, perfect. So here is what it says. It says if you define the sum, so if you have a set A plus B, is you do all the sums with elements of A and elements of B, then where A and B are non-empty, then the supremum of the sum is the sum of the supremums. And it's outlined right here how you could do it, okay? So let's remember that the supremum of the sum is the sum of the supremums. Could we maybe use these to our advantage, right? And the difference here is that we don't appear to have two supremums. So we'll take a look at that. So Now there's another one that I wanted to see. Where is it? Where is the one where you multiply by a constant? Must be somewhere around here. So that was 6. Oh, right here. Yes, that's it. This is the other one that I wanted. So it says, so this is the one that we had on our exam, right? That we did it with the constant 2. The supremum of 2 times a is 2 times the supremum of a. And if the constant is positive. Now, it doesn't have anything with when the constant is negative, but I'm going to tell it to you what happens when the constant is negative. When the constant is negative, the supremum of CA becomes the C times the infimum of A, all right? The inequality flips. That's what happens. All right, great. So let's remember those. I'm gonna write them now in the page. So these are a few of interesting things we learned that, I mean, we should know already, but it's been so long that maybe we don't remember. So it's the supremum of A plus B is the supremum of A plus the supremum of B, and also the supremum of K times A equals K times the supremum of A if K is positive, or K times the infimum of A if K is negative. All right, so now let's go back to this over here, right? So what is it that we want to show? We want to show this capital M minus this little m, right? And what is the issue here? The issue here is that this one, so what is, let me see. So I want to change this to, so what is negative m prime, right? M minus little m. So m minus little m. So m is the supremum of something, of the f. You can think of this as the supremum of the set f of a, right? Of the image of a. And then, oops, I didn't put the, so this is just m. How about little m? So little m is the infimum, but I want minus little m. So minus little m is the supremum of, sorry, is the infimum. It's minus the infimum of x in a, right? And what is it that we said over here, right? I want to use this property. If the k is negative, in this case, the k is negative 1. So if k is negative and k times the infimum is the same as the supremum of minus a. So this is actually the supremum of minus f of a. Is that clear? By this property over here. So then if I do m minus m is the supremum of these two, which I can make it by this property over here. The supremum is the supremum of the sum. So this is the supremum of f of a plus negative f of a. Now remember, these are sets. So this is this interpretation. Let me write it here. This is the supremum of f of a minus f of b over all pairs AB in capital A. That's really what we're doing, all right? That's little m, capital M minus little m, right? And if I do it now with the primes, so similarly, if you do it with the primes, m prime minus little m prime is going to be the supremum. This time with the difference is that we have the absolute value function. So it's really the absolute value function evaluated in A plus negative of the absolute value function evaluated in A. So that's the supremum of the absolute value of f of A minus the absolute value of f of B. Okay, and what we were asked to show is if we can know that this number is bigger than that one, right? And it's gonna turn out to be the triangle inequality once we realize. So how do we know that this supremum is bigger than this? And the reason is that term by term, I believe. So there is the issue of whenever, so you can assume that f of a is bigger than f of b. Otherwise, it won't be the supremum, right? So some of these numbers, if this number is negative, you can flip it, and then it's going to be positive. So you can change a by b and b by a, because you're going over all pairs. So you can assume that these numbers are positive. So then all we need to show is that this number is in fact bigger than these ones over here. And that is true because by the triangle inequality, f of a minus f of b plus f of b is bigger than f of a, right? That's a triangle inequality for arbitrary numbers. And then because this happens, we know that this number is bigger than f of a minus f of b, right? So, and like I was saying, this number is this one over here. The supremum has to happen when the numbers are positive. So if this for the numbers that are positive, this is the same as f of a minus f of b. If f of the a is bigger than f of b. And if f of a is not bigger than f of b, don't consider that pair, right? Don't consider that pair. That pair definitely will not contribute to the supremum. So that's it. So all of these, every one of the numbers that count in here are bigger than the numbers than all the numbers in here. So therefore, this set, the supremum of this set has to be bigger than the supremum of that set. So hence, m minus little m is bigger than m prime minus little m prime. Okay, and that's a proof of that part A. Now, it's not clear at all right now why would we need that part A to show what we want, right? So let's see if we are going to have the time or not. I think we do. Okay, so now let's go back. Oof. What was our page? We were now kind of like near the end. Let me see. Right over here. Good. Good. So we proved part A. So capital M minus little m is bigger than capital M prime minus little m prime. Now it says show that if f is integrable, then absolute value of f is also integrable. So let's try to see what would be the definition. How do we check that capital F is integrable, right? So if we just wanted to do it from scratch, how would we do it, right? So now this is for part B. So assume f is integrable. Then we know that absolute value on the interval AB, of course, absolute value of f is integrable on AB if and only if for every epsilon, right, we're going to use the integrability criterion, there exists some partition P epsilon such that the upper sum of absolute value P epsilon minus the lower sum of absolute value P epsilon is less than epsilon, right? If this happens, we're done. If we could show this happens, we would be done, right? Okay, good. So now what? Well, what is this guy over here? Let's write it down. So it's the sum. It's a sum, right? It's a sum over, if, as usual, we assume that P epsilon. So P epsilon, we assume that this is A, which is x0, and then less than x1, less than xk, which is b. So this will be from 1 to xn, my bad. From 1 to n of mk, right? But it's not really mk. According to our previous definition, is the one with absolute value. So it's mk prime, right? The primes are the ones that had absolute value, times xk minus 1, right? And similarly for the L. Yes? So we're almost done. All we need to do is use our inequality, right? So what is our inequality? We have it right here. In general, it doesn't matter what kind of what kind of set you have. This happens. The m prime minus the little m prime is less than or equal m minus m. Okay, so then what happens when you do u minus L? Write it here. This is going to be the sum from 1 to n of mk prime minus little mk prime times xk minus 1. Ah, but now we're going to use our inequality, right? So these mk primes minus little m, the capital M prime minus little m prime is less than or equal m minus little m. So this is less than or equal capital M minus little m. And if you unpack this is exactly u of f minus L of f. And we already know that the f is integrable, right? That's our assumption. So because f is integrable, we know there is a p epsilon partition that makes this less than epsilon. So we know this is less than epsilon because f is integrable. So I'm not being precisely writing it here. So technically I should have started. I mean, we discovered now how to do the proof, right? Here's how the proof should be written correctly. You say the following. You say f is integrable, and because f is integrable, there is a partition p epsilon that makes this happen. This one over here. That makes this happen. Then you calculate u of capital F minus L of capital F with, of absolute value of f. You know that this is the one with the primes. The primes by part A satisfy this inequality. And then this is this one, and this one is less than epsilon by assumption. Therefore, this one with the one with absolute value of f is less than epsilon. It follows that. Therefore, absolute value of f is integrable in AB. And we are done. All right. Okay. I have only, before we go, you know, it's already time, but let me just show you a couple of definitions that we're going to need for next class to do the fundamental theorem. And they're right here. They're super easy. So these are simply definitions. And it's to define what happens. So we only define the integral of AB when A is less than B. And you'll know this from regular calculus classes, so I didn't think that it was going to be that difficult to emphasize it, but so I'm just going to show it to you on the screen. Then what happens when they are reversed? And by definition, so this is just a definition, by definition, if you have a bigger one in the bottom, if you do from B to A, then you reverse them and you pay a negative sign. So you do minus the integral from A to B. And we also define the integral from C to C, if the numbers are the same, to be 0. Okay, so we're going to need that for next class. And this is it for today. So we'll continue tomorrow. I mean, not tomorrow, in Thursday, and by then I hope that you already will have your scores for the exam we just had. All right. Any quick questions before we log off?
Thank you.
All right. Good, guys. See you in a couple of days.